Hey everyone, and welcome. Get ready because today we are pulling back the curtain on one of the coolest concepts in all of statistics. Seriously, it's like a statistical magic trick that finds perfect, predictable order where you'd swear there was only chaos.
So, let me ask you this. How is it possible that you can start with data that is just all over the place, totally lopsided, completely random, and somehow out of all that mess, create a beautiful, perfect, and predictable pattern? Well, that's the big puzzle we're going to solve together today.
To really get how this magic trick works, we have to start with the main ingredient. It's called a sampling distribution.
Okay, I know that sounds super technical, but trust me, it's not. All it means is that we're not going to look at single data points one by one. Instead, we're going to look at the averages of lots of little groups. Imagine a huge jar of M&Ms. A sampling distribution isn't about one single M&M. It's about what happens when you grab a handful, find the average weight of that handful, write it down, and then do it again and again and again.
All right, now that we've got that down, it is time for the big reveal, the secret behind the whole trick. This is it, the central limit theorem. So here's the secret sauce. The central limit theorem says that if you take a bunch of random samples from any population, and I mean any, it could be the weirdest shaped data you've ever seen, and if those samples are big enough, the averages of those samples will always form a beautiful, normal bell curve. And that right there is the magic. The key part is no matter what the original population looks like, you can start with a total mess, but the averages will create perfect order. Okay, I know that still might sound a little bit out there, so let's just watch it happen. Let's tell a story and build one of these sampling distributions from the ground up. So our story starts here with this population. And as you can see, it's not normal at all. It's heavily skewed with most of the data crammed over on one side. It's lopsided and totally unpredictable. This is our messy, random starting point. So here's what we're going to do. First, we'll dip into that messy data and pull out a random sample. Then we find the average of just that sample. We take that average and we make a single dot on a new graph. And then we do it all over again and again and again, like hundreds, maybe thousands of times. And boom, this is what happens. After we've plotted all those different sample averages, look, the new graph doesn't look skewed anymore at all. It's a nearly perfect bell curve, centered right around the true average of the whole population. We started with chaos and ended up with this beautiful, predictable shape. It's pretty amazing, right? This is the million-dollar question, isn't it? We saw the magic happen. But remember that little condition? The sample size has to be large enough. So, what does that actually mean? How big is large enough? Well, you're going to love this. It turns out, for pretty much all of statistics, there's a simple, super powerful rule of thumb. A single number that's the key to making all this magic happen. 30. That's it. 30 is the magic number. And this rule right here seals the deal. As long as your sample size, which we call n, is 30 or bigger, you can basically guarantee that the distribution of your sample averages is going to look like a normal curve. It's the key that unlocks everything. All right, let's see this rule in action. We'll run through 3 quick examples to see what happens when we're below 30, when we hit 30, and then a cool little shortcut. So, example 1. Let's say we go back to our skewed population, but this time our samples are small, less than 30. Well, look what happens. The magic just fails. The result is still a messy, lopsided shape. It's not normal, and you can't really rely on it to make any good predictions. A small sample just isn't strong enough. But now, watch what happens the second we cross that magic line. We're still starting with that same skewed data, but this time our sample size is 30 or more. And just like that, we get our beautiful, predictable, normal curve. The central limit theorem kicks in, and suddenly we have something we can actually work with. Now for the shortcut. What if the data you're starting with is already nice and normal looking? Well, in that case, you get a free pass. You don't even need to worry about the number 30. Any sample size, even a really small one, will give you a perfect, normal sampling distribution. It's a nice little bonus. And this table here is the perfect cheat sheet. It sums it all up. Start skewed with a small sample, you get a mess. Start skewed but use a big sample, 30 or more, you get that nice, normal curve. And if you're lucky and start with a normal population, any sample size works perfectly. Easy, right? Okay, so we've seen the trick, we've learned the rules, but what's the big deal? Why is this considered one of the most important ideas in all of statistics? Why do we even care? Well, It all comes down to the power of prediction. The central limit theorem lets us take a small, easy-to-get sample and use it to make really confident guesses about a massive population. Think about it. A pollster doesn't need to ask every single voter in a country. They can survey a few thousand. A scientist doesn't need to measure every star in a galaxy. It's the foundation for so many scientific discoveries and business decisions. It lets us turn the unknown into something we can actually understand and predict.
So I'll just leave you with this. What this theorem really shows us is that underneath a lot of what looks like total randomness, there's often a hidden, predictable order, just waiting to be found. So now that you know the secret, now that you know the magic of the number 30, what hidden patterns out there in the world might you start to see in a whole new way?